So I'm going to talk about language model alignment, which is going to basically play with the kind of loyalty aspect of what Pramod talked about. I didn't know the audience, so it might be a little bit narrow, so I apologize in advance. So alignment is basically this concept where we want to make models more fair, more safe, more trustworthy, remove hallucinations, or maybe we want to personalize the models. So it has been around for many, many years. It has researched in the ML community in the past few years. So I'm going to try to go into the basics of alignment and hopefully actually give you a new alignment method that's going to be useful for personalization of the models. So before jumping in, generally when we're doing language model training, there are 3 stages of training that we go through. The first stage is pre-training, where we train on large amounts of data. It's long turnaround. Generally, we not very controllable. Maybe we do it once. Then the next stage is supervised fine-tuning, where we actually have some specialized data that has some particular style that we want to imitate. So we put that into the training stack. It has shorter turnaround. It makes it easier to steer model to desired behaviors. And the last stage is alignment, which is also called preference optimization, where now we want to actually train on pairs of positive and negative data. So here we are also going to be able to learn from behaviors that we don't want to see. It has much shorter turnaround. It's basically we train for very few number of steps, and it basically applies the final touches, and that's basically the stage of training I'm going to talk about. Okay, so an example of alignment, let's say we have already trained a language model, and then I'm going to prompt it with tell me a joke, and then the language model is going to generate a joke. But let's say we want to make sure that the joke doesn't have any racism, no stereotyping or profanity. So the question is, how do we do that? So in order to do that, we generally look for something called a reward model. So reward model is a scalar that captures, basically can score the input and output and give it a scalar number. That the scalar, it's very similar to the ELO rating. Basically, when you have a scalar for 2 different outcomes, then when you put it together, it's going to model the probability that one of them is actually preferred over the other one. Now, this could be in the context of safety or in any other context that we were going to do alignment. And generally, basically, this is called the Bradley-Terry model, using which we kind of train this reward model. Now, given a reward model, a very, very simple baseline for alignment is called best of n, where we're going to generate n responses from the base model. So this is the model that was SFT. You can generate n responses. You can rank them based on this scalar reward, pick the one that's best and serve that to the user. Turns out that this is very simple. It's actually, I'm going to talk about the fact that this is seemingly stupid baseline is very, very effective, but it's very expensive in terms of throughput because now you have to do the inference n times. It's also incompatible with streaming. So I think Tirtha was talking about the autoregressive nature of decoding, and then you want to actually be able to serve the tokens as they're being decoded. And this best of n doesn't allow that. Now, if you are familiar with alignment literature, so there is a lot of XPO algorithms that are coming out. All of them are, in a sense, solving a reinforcement learning problem with some regularization where you want to make sure that your model doesn't drift away from the base model much. Now, this is basically solving this problem is generally hard. I'm not going to go through it. much, but it's very easy to serve because now once you solve this problem, you get a new model. You can it's plug and play with the old model, and you can just serve it. There are many more alignment methods. I'm going to briefly mention the direct preference optimization, where basically what you do is you take the Bradley-Terry model optimization, and then you take a closed form solution basically for your reward optimization, and then you plug it in, and you will be able to solve that problem. And there's many more kind of alignment techniques. So we are today going to talk about yet another alignment technique, which we call control decoding. So control decoding is based on the fact that we make a very simple observation where you can actually write down a token-wise Markov decision process for language model where state is now going to be a prompt plus tokens decoded so far. So again, Tirta mentioned that decoding happens token by token, so you can think of tokens being words. And the action that we're going to take is the next token that we're going to try to decode. And a notion of policy in this case is the distribution over the next token, given this state, which is the prompt plus whatever has been decoded so far. And then if it turns out that this has a closed form solution, and the closed form solution is basically given in this form, where the align model is basically equal to the base model, exponentially tilted with what's called the value function for the reward. And the value function for the reward is basically just determines the expected reward if we decode from a certain state. So let's say in the context of tell me a joke, then the value function determines what's the probability that the joke is going to be safe, given that I'm just going to follow the base model's kind of language policy. With this observation, so the entire kind of alignment boils down to learning this value function. And now if we've learned this value function separately from the base model, there are many advantages. One of them is that it's going to be modular because now we have two separate models that we can combine. Maybe it's personalizable. Each user can have its own value function, and then we can actually do those value functions maybe on device, that the large model may be on server, and those could be combined and so on and so forth. So I'm not going to go into the details of serving it, but I'm going to try to tell you how we can train the value function. Now, the first thing that you may come to mind is that, okay, we can actually use the Bellman identity, and very similar to how DQN was used to solve Atari games, we can just basically go through. So the math is very similar. We can try to actually go through the exact same math and try to solve the Bellman identity. And it turns out that this very simple first step actually works. And now, so once we have actually trained the value function, then the next question is, how do we use it in practice? So as I said, since this is a separate model, and the base policy is another model, so we're going to try to to basically first get logits from the base model. So these are likelihoods from the base model. So I'm going to reuse Tirtha's example. Sorry? Not for your paper. This is for yes. So I so we actually did reuse. This is reuse Tirtha's paper example. So this paper will be liked, disliked, reviewed, hated. So let's say hated has the highest likelihood, but then we're going to also get the sentiment score here. Let's say we want to have the highest, best, most positive sentiment. So that's coming from the value function. We're going to linearly combine those scores, and then we're going to get an aligned score, and then we're going to sample from that. Okay, so this is basically what I call the token-wise decoding from this model. I'm going to also introduce a different variant of it, which is called block-wise decoding. So if you remember, best of n is sequence-wise decoding. So you're generating a full sequence, and then you're going to be ranking them based on the reward, and then keeping the best one. Now we're going to do something similar, but in a blockwise manner. So we're going to generate a block of, let's say, 4 tokens, and then we're going to do it 4 times, and then keep the one that has the highest value, and then drop the rest, and then continue decoding. So that's, in this case, again, the same example. Will this paper get accepted? This paper will be liked by, has the highest sentiment, so that's the one that we're going to keep. We're going to drop the rest of the decoding path, and then we're going to continue from here. Okay, so this has advantages over best of n. The most obvious one is that it enables basically streaming, so limits the user-facing latency to decoding a single block, and it makes a large effective n practically feasible. How much time do I have? 10 minutes. Now, how do we evaluate alignment methods? So, okay, so we are sitting in a lab. We're trying to train a new model. You train a new model. The best case scenario is to get human evaluations. Human evaluation takes time. The second best case scenario is that if we have some automatic metrics that are correlated with the human judgments. So that may or may not always be available, but we can actually have some surrogates. And the surrogate that we're going to use is basically this two-dimensional kind of trade-off plane that we're going to look at. On the x-axis, we are looking at the KL divergence between the new model and the old model. So we want to make sure that we're not drifting much from the old model. And the reason is that we don't want to use the capabilities that are encoded in the old model, because these rewards are extremely noisy. And so it's very quickly we're going to overfit to those rewards. And on the y-axis, we are going to plot what's called the win rate against base model. So we're going to draw one sample from the new model, the one sample from the old model, and we're going to look at basically have a judge to say which one is better in terms of the reward that we have. Generally, we use a different judge. Maybe our auto eval metrics than the one that we use for training. And then we're going to operate in this trade-off plane. And so the goal is to be able to get the highest win rate with the lowest amount of KL. So that's going to be the desired kind of operation point. Now, estimating KL divergence is generally simple if we have the new model's logic. So if a new model gives us basically is trained already, so we can actually roll it out, basically draw a sample from the new model, and then we're going to take the log likelihood ratio between the sample under the new model and the old model, and that's going to give us an unbiased estimate of the KL divergence. But that's not always possible. So I talked about best of n. We don't have the logics of best of n model. So the question is how can we estimate the KL divergence for the best of n model? And by induction, also the blockwise control decoding, we don't know how to compute the KL divergence. So it turns out that there is an analytical formula that has been appearing in the literature that claims that the scale divergence is log n minus 1 over n. Remarkably, doesn't depend on anything. It just depends on n for best of n. So I think it was natural for us to ask whether this formula is actually true. And so it turns out that you can construct a binary language model where we can compute and then in this binary language model, let's say it's zeros and ones, one is preferred. We can actually compute exactly the best of n distribution. We can compute the KL divergence, and turns out that the formula is wrong. So then the question was, okay, so what is this what can we do with this formula? Turns out that it's at least the good news is that it's an upper bound on the KL divergence. So we were able to prove that, and then it's a decent estimate of the KL divergence if the probabilities of outcomes of the language model are small. So we think of it as creative language models have basically are not deterministic. So this scale divergence formula is not far from reality. Now, okay, I'm not going to go into the details. So I'm an information theory background. We should have some some formulas that we're going to skip in the interest of time. Now, okay, so back to this kind of trade-off plane where we wanted to look at win rate here. I'm looking at expected reward versus scale trade-off, and that's basically the picture that we are going to look at. So here, the y-axis is normalized length. In this case, we wanted to actually increase the length of generation. The takeaway here is that best of n is actually empirically the best method that you have out there. Most of these PO algorithms, so these are like state-of-the-art algorithms that have been published recently, are pretty much the same. So we are kind of on in terms of algorithmic advancements. I think we are not really making much progress. The token-wise CD is similar. It's kind of also similar to these other algorithms. Block-wise control, in a sense, bridges the gap between best of n and the token-wise control algorithms. It allows us to get much better performance. And this picture is very similar. So here we are looking at something called helpfulness and harmlessness reward from Anthropic. This is basically a typical kind of benchmark for language model alignment. We see similar behavior. Everybody is kind of within noise of each other, and then like best of n is actually outperforming every other algorithm. So the other pieces were, so now that we have this separate language model, separate value function, we can actually have two different value functions and then basically combine them with the base model. And here we're compensating for the length increase when we are improving helpfulness. So it's known that basically helpfulness reward is correlated with length. So if you want to increase helpfulness, you're going to have more lengthy generations. So we can actually use our length reward to compensate for that very quickly. Or we can actually take it and apply it to a new model without training. So this is a different model that was never used in training. And the remarkable thing is that the value function that's trained is for like a different model. And still, when we apply it to a different model that has never been seen before, it actually gives us very good performance out of the box. Or we can actually apply it to other kind of the DPO or other kind of alignment techniques. Now, one last thing I want to say is that basically it's the fact that best of n gives the better trade-offs is actually very remarkable, because if we solve this KL regularized reinforcement learning, this is just a strongly convex problem. So it should actually no other algorithm should be able to outperform it. But what happens is in practice is that empirically you can observe that best of n is very, very, very close to optimal. We had a paper at ISIT with Tirta that actually proves this for like a simple memoryless language model, that this is the case, that actually best of n is almost optimal. Okay, so in this very simplified picture, I didn't really go into a lot of practical issues. The rewards are noisy, so you need to actually deal with noisy rewards. Sometimes we want to kind of distill different preferences from an ensemble of rewards. There is multilingual cases. Sometimes we need to actually red team models to be able to get prompts that trigger the models, etc., etc. So there's many open problems still. And I think I want to end with, so hopefully I was able to convince you that best of n is the best thing that you can do. So start with best of n. If best of n works, it doesn't work, don't try any other fancy algorithm. None of them are going to work. And then also make sure to track your KL divergence in alignment. If it's above 8, probably you have already overfit. So acknowledgements, many excellent colleagues at Google, including Tirta. And these are some of the papers that we presented today. Thank you.